Well, let's follow on this beautiful geometric adventure, Michael. We've done the trig functions, sine and cosine, but there's another function that was related to the hyperbola.
That's right. So instead of working with the circle, x squared plus y squared equals 1, we can work with a hyperbola. So we just change the sign. X squared minus y squared is equal to 1.
So here's the canvas for you.
So here's what a hyperbola looks like. It's going to go through here, and there'll be another part over here. And the curve is given by x squared minus y squared is equal to 1.
So it's 1, so it's the unit hyperbola.
It's the unit hyperbola. You see when y is equal to 0, x has to be plus or minus 1. So this is the 1 here. Kind of like the circle across the x-axis at the point 1. And let's not worry about this side at all.
Yeah, so this is y, this is x.
Right. Now we're going to define the hyperbolic sine and hyperbolic cosine. It'll be just like this, the circle. We take a point on the curve. We're going to call this hyperbolic cosine of x, hyperbolic sine of x. Now the question is, what the heck is x? Any ideas, Matt?
Well, what if we go back to the circle?
Okay, do you remember what x was in the circle?
It was the angle, and we normally called theta. And the area was theta over 2 of our pizza slice.
That's right.
Well, the pizza slice here, if we join just like we did the circle, the pizza slice here looks weird because the pizza cutter made an arc here instead of straight down. He took off some that I wanted to eat, but now I've got to find the area of this. Now, we follow the circle, so we'll say x over 2 is that area.
That's right. So the area here is going to be x over 2. So that's how we define hyperbolic sine, hyperbolic cosine, in terms of an area. You give me a number, like 3. I'll say, okay, I'm going to take 3 over 2. I'm going to move this point until I get an area of exactly 3 over 2. And then that's going to be the hyperbolic cosine of that x value, hyperbolic sine of that x value. Make sense?
Yep, just like sine and cosine. Oh, the other thing is the circle was closed. This is open, so it's different that way.
It is different. So this point, as you follow this point, it can go all the way out to infinity.
And that's going to be one of the marked features of hyperbolas.
Yes, the hyperbolic cosine, hyperbolic sine, they can go off to infinity. Sine and cosine are always between 0 and 1.
Well, let's see where that takes us.
Okay, so what we want to do, like we did for the circle, is see if we can figure out the derivative of hyperbolic sine.
Let's go.
Do you remember drawing triangles?
I do. Let's do the triangles.
So there are 2 triangles we can draw. There's a bigger triangle. What's the area of this triangle?
Base times the height.
So the base is 1. The height is this guy. So this guy's area is base times height. Base is 1. Height is 6 h. And of course, it's a triangle, so we get half the area.
Right.
The smaller triangle we can get
Goes.
by drawing this line straight up here. Okay. So this point, the x position, the x position is 1. The height, that's a little bit tricky.
Yeah, so if the x position is 1 and we look at this, if we divide that by cosh, that'll be 1, so we'll get sinH over cosh. Looks like a tangent, but in hyperbolics.
In hyperbolics. So that's what this height is here. So this smaller area, base times height over 2, is going to give us what?
The tanH divided by 2, tanH of x.
So I'm going to say, I'm going to keep using my notation, sinh x over cosh x. And multiply by a half.
Yeah, that's great. Now the big triangle.
We got the big triangle. Its area is here. This is the small triangle. And this guy's in between.
Okay, so we're all good.
So let's write an inequality.
Yeah.
The small guy is this guy. a half sinh x over cosh x.
And that's less than x over 2.
So x over 2
And that's less than the big triangle.
sinh x over 2.
Well, here you also see another difference with the circle is before we had the small triangle and the big triangle was also vertical. But because this is curved, it's at an angle like
It's
that.
at an angle, that's right.
But also, we can kind of look at this triangle and kind of flip it around, and then it does look more like what you did before.
It does. It's very much like what we did before. And like we did before, we can get rid of these 1/2. So we have sinh x over x, sinh x over cosh x, smaller than x, smaller than sin x. Remember, we're trying to find a linear approximation for sin x, for x being small. Cosh x, when the area is 0, we're going to be at this point, so cosh would be 1. So this guy is very close to 1. So this is it's a very good approximation to say this is approximately sinh of h divided by 1. So it's not quite less than or equal, but pretty close. Less than or equal to x, less than or equal to sinh x. So what do you think our linear approximation to sinh x is going to be?
Well, we got the sandwich theorem. It's greater than this and less than the same thing, so there's your answer.
That's right. So it looks like sinh x is approximately x.
For x small.
So we can say sinh x is approximately equal to x. Think of that as 1 times x. There's our line. What's our slope?
Slope of 1.
So that tells us its derivative is 1.
Right.
I should write it down so we have it somewhere. Of sinh x at x equals 0 is 1.
So now can we go and copy what we did before when we move away from sinh x near x equals 0?
We can do that.
We need the magic formula for...
We do need the magic formula. Let's do that right now.
Okay.
So, magic formula. Well, the surprising thing is it's the same formula. For sin x, it's the same formula.
So
We
we're
can
going to
explain
use
that.
it first and explain it later.
Exactly. So here's the magic formula. Hyperbolic sine of x0 plus x. It looks exactly the same as for sine.
Except sinages and coshes.
Exactly. So sinh x naught, cosh x naught.
Cosh x.
Thank you, Matt. Plus cosh x0 sinh x.
Right.
We do our approximation. Okay. This we haven't actually said, but it turns out the same. It's approximately 1 plus 0 times x. So it's a flat line.
Yep.
That's our approximation. This approximation we saw already. It's approximately x.
Yep.
So what we get in our approximation is this is approximately sinh x0 times 1 plus cosh x0 times x.
Now you're going to subtract this to the other side, and this is our linear approximation with slope cosh of x naught, the derivative of sinage at x naught.
That's right. So now, for general x naught, the derivative is cosh.
Right? Oh, derivative of, yes, for general signage. Yep. Okay.
I'm going to throw in one little thing. If we try to compute the derivative of hyperbolic cosine, it turns out its derivative is plus hyperbolic sine. So the minus sign in the trig functions goes away.
Oh, so we can have a rotation matrix for hyperbolic functions.
We'll see that next time.
Great.